So on to this afternoon session where we have two more presentations for you. And the first one, we have Dr. Xuekun Liu from University College London, UCL. Dr. Liu has been working on CT and image-based modelling since his PhD, supervised by Professor Phil Withers at the University of Manchester, who is also one of the internal examiners on my PhD when I did that at Manchester. After his graduation in 2015, he joined UCL as a PDRA, actively engaged in 3D characterization, CFD and multiphysics modeling of energy storage materials. At the moment, he is involved in the project Multiscale modeling of lithium-ion batteries, funded by the Faraday Institution, and also working at MPL with a measurement fellowship. So thank you very much for joining us today. Please take it away. Hopefully it'll be as smooth as the first session this morning with no technical issues.
Let me share my screen now.
Yes, I've made you co-host, so that should be fine.
Yeah. So can you see my screen now?
Yes, we can see that.
Great. Just 1 second. Cool. Good afternoon, everyone. I'm Xuekun Liu. So it's my pleasure today to give a presentation about my recent work using Xyct techniques and image-based modeling to understand the 3D microstructure design of the lithium-ion battery electrode. I also would like to thank Helium for organizing this online forum. It's really a great effort, and also thank you for your introduction. So, Helene has already introduced on behalf of me. So because this is my first time joining this event. So as he said, during my PhD, I mainly used Xyct to study the biological material, the failure mechanism, and the mechanical response. Then I joined UCL after I got my PhD and started to use image-based modeling since then to understand and design the hierarchically structured porous material to enhance mass transport in the solid acid fuel cells and also in the skeletons scaffold. Then I got the measurement fellowship in MPL. Since last year, I have been working part-time at the UCL and part-time at MPL. So my talks start with a basic introduction of the lithium-ion battery and the imaging challenges. Then the 3D microstructure characterization, the image-based simulation of the state-of-the-art electrode. In the end, I will try to use this technique to explore some advanced microstructure to improve the performance. I know some of the people in the audience come from different areas, so I will try to use the most simple and basic language to explain some this content so that you won't get drifted away from content. And my research interest lies in linking the fabrication with the microstructure of the electrode, and then to correlate the mass transport and the reaction kinetics with the 3D microstructure of the electrode to see how it affects the battery performance. Then we can get more insights to optimize the fabrication process to improve the battery performance. This is the basic schematics of the structure of the lithium-ion battery. It mainly consists of the anode. We normally use graphite, and the cathode. Cathode is made of the lithium transition metal and the oxygen compound. So this is the SVM image, shows the morphology of the graphite and the state-of-the-art cathode, which is the compound consists of the lithium, nickel, manganese, cobalt, oxygen. So we also name it NMC. The battery is filled with the electrolyte, which works as the to deliver the charged carrier, which is the lithium ion, to deliver it to transport between the cathode and the anode. So when we charge the battery, we apply the external potential to drive the electron to go through the external circuit, and the electron will meet with the lithium ions, which transport inside of the battery and the lithium-ion get intercalated into the anode. When we discharge the battery, the process goes in the opposite way, and by connecting this load. So the key parameters to use to design the electrodes, one is the porosity. So the porosity affects the mass transport in the pore phases. As we can see here, this yellow line indicates the tortuous pathways for the electrolyte flow from the one side to the other side. If this porosity is too low, or if the is too tortuous, then we can get some depletion of the reactants at the end of the electrode. It also affects the activation, the active reaction area density. The other parameter is the particle size. It affects the lithium transport in the solid phase, and also the electronic conducting network and the active reaction area as well. So depending on the applications, a battery can be classified into two major groups. One is the high energy density oriented. The other one is high power density oriented. So for the high energy application, most of the time people fabricate the electrode with high volume fraction of the active material and a thick and a low porosity. For the high power application, the transport of this reactant is the key effect. So we tend to fabricate the electrode with thin thickness, high porosity, and small particle size.
Hi. I think your microphone is kind of going in and out. So is there
really?
Yeah, I mean, it's mostly followable, but it dips in and out. So I'm not sure if you're using the microphone on your headphones.
No, it's this in-ear phone.
Maybe it's moving about a lot. I'm not sure, but we'll try and carry on.
Okay. If it's not tolerable, I will try maybe unplug this and see if, yeah. Sorry about this. I didn't know this could be an issue. Sorry about that.
That's okay.
So this is the overview of the Xyct Lab in UCL. We got the industrial CT, the micro CT, the Zeiss X-ray Versa, and also the ultra, this is the nano CT. Because of this because of these three microscopies, we can cover a really wide range of the resolution and the energy of the X-ray. So we can investigate the battery at a multi-length scale. The first is the industrial CT scan of the cylindrical battery. And you can see these main components, this shell and the venting disc and the current collector. The zoomed in image shows the parallelly aligned electrode with the current collector and this electrode, but the resolution is not high enough to resolve the details. So we need the help of the nano CT, so we can see the details of the microstructure of the electrode, the graphite, the separator, and the cathode material. The separator is used to separate the two components in case they got short circuit. So here's a slice of the cathode NMC cathode. You can see this easily to distinguish between each phases. So we can use basic segmentation, the thresholding method, to segment out this particle. And also for the dark area, this is a macro pore inside. And then between them, we see these cloudy phases. Actually, this is the carbon binder or carbon. This is added into the electrode to enhance the electronic conductivity. And because the microstructure is too fine, and also the carbon is really low X-ray attenuating, when it is scanned with this high X-ray attenuating NMC cathode, then the contrast gets really bad. So we came up with a solution with this dual scan superimposition technique. So we scanned the second, we did the second scan with the standalone carbon phase. And this is what the microstructure we capture using this scan. So then we can superimpose this new data with the previous low contrast data to fully reconstruct the 3D microstructure. With this technique, then we can conduct the full 3D microstructure characterization and image-based simulation. So this, the first is the volume rendering of the grayscale data. Then we segmented it into three phases. The blue phase is pore, green is carbon, and the rest, the gray, is NMC or active material. So this figure visualizes the pore side distribution. in the cathode with the color map superimposed onto this pore face. Then we can conduct the CFD simulation along the current flow direction and the other two directions as well. So we can extract the tortuosity distribution in the 3 directions, and we see along the current flow direction it has much higher or slightly higher tortuosity compared to the other two because of the manufacturing process. Then we also can notice this locally high bright area. This is related to the pore bottleneck effect, which gives a locally high flux. Then we also can identify every individual particles. Then by extracting the eigenvalues and the eigenvector using the image analysis techniques, we can extract the orientation, the shape, and also the size of the particle. They are represented by the template, the cylindrical template here. Then we can quantify the particle diameter distribution as a function of the distance to the separator. The separator is at the top, which is the entrance of this electrode. And what we can see, and this symbol size proportionally related to the particle size. At each depth of the electrode, we see that it consists of the large particle, small particle, medium particle, small particle, from 2 micron to 14 micron. But across the depth, we see it's quite consistent. We also can analyze the shape distribution. We found for smaller particles, it more tend to be flake shape compared to the larger particle, which is more spherical. This is the orientation distribution projected on the 2D map. We see this more or less random distribution. And here we also can analyze the porosity and the pore size distribution in 3 orthogonal planes. And we notice this large fluctuation of the porosity and also the pore size as well. This indicates the microstructure is not homogeneous. And this figure shows the correlates the tortuosity as a function of the porosity. Then after we segment the pore face, we imported into the meshing software. We use simpleware scan IP, and we can see here. We can see this adaptive mesh element is used with the coarse microstructure. We have coarse mesh size, and the fine structure we use fine size. And then we import the meshed volume into the console multiphysics, which is a multiphysics simulation software. This is the physical process of when we discharge a battery. You see, lithium-ion transport through this blue phase, which is the pore, meet the electrons and then intercalate into the active material. Then we use a range of different partial differential equations to solve 5 dependent variables. They are the concentration of the lithium, the charge, the potential of the electrons in the particle, and the potential in the carbon, and the electrolyte concentration and the potential in the electrolyte. And then we found this simulation result is in good agreement with the experiment. Then let's go to the visualization. Yeah.
Your audio is still cutting. There is a option in the settings that might be worth.
Yeah.
There's an automatically adjust microphone volume.
I think I came across this before. I think it's maybe partly because people keep flowing into the room because I'm keep clicking admit the entrance of the room. Maybe that is the reason. I don't know.
Maybe.
Yeah, because I also
if you just ignore them,
yeah.
And then
because it appears on my screen, so I have to click admit.
Yeah, because we had to give you co-host permission to share your screen, so you just ignore them.
Okay.
And yeah.
Okay. Yeah.
Do you want to try changing the settings? So if you go.
Yeah.
Audio settings. So from your microphone in the bottom left.
1 second. Yeah. Bottom left.
And then there's audio settings.
Yeah.
Then under microphone, there's a automatically adjust microphone volume. Maybe if you
yeah, I have already ticked it. Should I?
Okay.
It?
or maybe if it's unchecked, then maybe it should be checked to do.
Okay. Yeah, I have unticked it.
Okay.
Yeah.
Right.
Should
Well,
we go?
we'll try carrying on. But
Yes.
about people coming and leaving the room, we'll sort that on your behalf.
Okay. Okay. I will just ignore all of the entrance from yeah. Sorry about this.
No, sorry about the interruption. Please.
It's okay.
Continue.
It's okay. Okay. Can you see the slide now?
Yeah, we can see your screen okay now.
Okay. So here, what I show here is the simulation results of the current flow, and also the current flow from the top to the bottom. And here the C rate means the current that need how large the current is. If it's 1 C discharge, that means we discharge the full capacity of the battery in 1 hour. If we enlarge this current by 5 times, if it's 5 C, so the full capacity of the battery will be depleted in 12 minutes. So here we see that with the low C rates, we get a more uniform lithiation of the particle. That means all of the particles are well utilized to host this lithium and to intercalate. But with the high C rate, we see it builds a gradient from the top to the bottom. The top means is more lithiated compared to the bottom. This is because of the electrolyte concentration distribution as a function of the C rate. If the current is high, then this at the bottom, the reactant depleted more fast. Because of the insufficiency of the reactants, then the reaction here is less active. Then we also notice this high concentration of the lithium-ion flux when the C rate is high, noted here by using this red color or the color map. This is really detrimental to the battery operation because this high lithium-ion flux means that locally the ion transport is really high resistance. It generates high ohmic heat. And then the last column is the charge transfer distribution on the surface of the active material. Here is the red means the reaction is more active compared to the blue region. This is also need to be avoided because if some particles are more reactive compared to the other one, then we will have uneven degradation or aging of the battery. Then we also can analyze the individual particle, the performance of individual particle as a function of the particle size and also the position of the particle. Here, the symbol size again proportionally represent the particle size. We see at the low C rate compared to the high C rate, the gradient starts to build up gradually as is consistent with here. Then for the larger particles, the color is blue, means it's underutilized, or we say the concentration inside the particle is really low. That means when the battery has been fully discharged, then we still have really unutilized active material. This means that the car will drive less far compared to this if we use small particles. And this histogram distribution shows that how uniform the lithiation takes place. And this the green peak, for example, shows that at the bottom of this electrodes, then we have low lithiation compared to the top of the electrode. Then if we overlay this three together, we see at different C rates this trend of the gradient of the lithiation. Then we are also keen to understand why this reaction is heterogeneous inside of the electrode. Here, the top is the charge transfer, we say the reaction currents, and the bottom two volume, this is the exchange current density, which is the parameter related to the local concentration of the electrolyte. And here is the driving force. Then we conduct the 2D histogram correlation. This is to analyze the colocalization of these two distributions, as we see here. And what we found here is that the charge transfer current density distribution is more correlated with this driving force instead of the exchange current density. And this is mainly affected by the potential in the interface of the electrode. This potential is related to the mass transport property inside of the pore phase. Here, the pore phase is color-coded to show the travel distance from the top at the entrance of the electrode to the bottom You see it's more far away, so this is red. Even at this small area, you see at the same height, you see this is larger, or the more red means it's more travel distance, longer compared to here. This is because of the local difference of the tortuosity or because of morphology of the pore. As you can see here, the reacting surface, this is longer compared to here. Then this corresponds to here. This is a lower potential, then this gives a higher current distribution or higher exchange current. So this is responsible for the heterogeneity of the reaction. Then building on this insight, we can suggest a new electrode to improve the battery performance. So here you see at the top, this is the original as prepared electrodes with the simulation result here. Then by using morphological operation of the image analysis, we can generate a layer which is about 15 microns with a much smaller particle size but the same volume fraction. And this can be easily to compare by the color and the morphology of the particle. As a consequence, we see we get a much higher reaction area and a much larger mass transport property at this region. We see it's more smooth gradient of the electrolyte. And then we also can we get more reaction area, then that means the loss of the voltage has been suppressed. You see also it's more uniform distribution of the current density compared to here. Then it's more uniform lithiated compared to the original large particle. Because if the particle is large, then the lithium-ion has to transport long way. If it's long, that means the resistance is very high, so it generates much less inferior capacity of performance. This is the comparison of the original microstructure with the improved structure. This is the high difference of the voltage and also the capacity. The second microstructure we explore this the gradient pore size distribution or porosity by dilation the pore size by 250 nanometers at the region and close to the separator 20 microns away and 30 microns away. We got this gradient pore size distribution as we can see here. The first sample has a high porosity at the beginning, the second sample has high porosity in the middle. Then we found out that only the porosity at the top surface or close to the entrance of the electrode significantly affect the performance of the battery. This is because we have higher concentration of the electrolyte here compared to the other two. Here, the R123 corresponds to this R123. You see this much improved performance. And then we can conduct a bunch of different investigations on different microstructures. For example, just gradient particle size, gradient pore size or porosity, and high porosity sample or thick electrode, and as prepare the electrode. And we see this, we plot this specific power with against a specific energy. We see different trends as well. Then here, these three volumes here, we can see that volume 1 is the as prepared sample. Volume 2 is the high porosity sample. At the same series, you see how more uniform it is when we use high porosity compared to the original design. Even for the high porosity sample, if we increase this current, we see also this intraparticle and then the interparticle difference of the lithiation and underutilization of the active material. So I know I talked very fast. If you are more interested in this work, you can find the more details in this paper published several months ago. So in the end, I would like to use a video to summarize the work in this presentation. So first you see is the whole battery scan using the industrial city, and the resolution is about 16 microns. And we can easily identify different components in the battery. Then we did the high resolution scan to resolve the more details of the cathode and the anode. Here is rendering the green phase, which is the pore morphology in the three phases. You can see it's quite different in the three components. And now it's rendering the pore size distribution using the skeletons. They are, and you can see some of the pores are more horizontally aligned. Some of them are just a random distribution. And this is the particle orientation and morphology and extraction. Then based on this, we can conduct this image-based in this battery. So this is a brief summary. First is we can use dual scan superimposition technique to solve the problem of the imaging challenge if the material has multi-length scale microstructure and weak contrast. Then we operation such as the uneven aging, the local heating, and also underutilization of the active material. Then we, by using the image-based simulation, we can create some new microstructure and to first validate if that is really helpful for the battery performance. Then apart from that, we also can use image-based simulation to check the manufacturing process in the battery fabrication, such as what is the powder mixing and drying, and the temperature selection, and also the coating and the densification process as well. So my latest work has been already in the last stage of the publication. Is using the in situ calendaring the microstructure in 3D and how it affects the performance. And in the end, I would like to thank my collaborators from UCL, from America, and from Italy. And this is the end of my presentation. Thank you for your listening. And I'm really sorry about the problem of the sound. I didn't imagine that. Thank you very much.
Right. Well, thank you very much for that. Can I ask you to stop sharing your screen, because it also stopped a bit at the end, but hopefully maybe that will help the audio. We started a little bit late on that one, so we do have time for a few questions. As before, the first instance, could you pop it in the text chat, and we'll try to field those questions and see how it goes with the audio.
At the moment, my computer is a little bit freezed. I clicked on the chat, but that circle is still, yeah. Could you please read out the question, as I can't see it at the moment?
Yeah, I'll read it out as I can. While we're waiting for maybe potentially a few people to ask questions. So I wanted to ask you with regards to, so you said you're using ScanIP to do the meshing.
Yeah.
Did you mention what you were using to run the simulation?
Yeah, I mentioned the console multiphysics software. Yeah.
So what would you say is the biggest challenge you had in setting up the simulation versus a normal kind of CAD-based simulation?
Because the normal, I didn't, because we did the simulation based on the real microstructure of the Xyct. It definitely has more problem compared to the CAD version of the microstructure. The first is the fine microstructure in the volume, because I found out that if you have like a porosity which are not connected to each other, if it's like a small island and it's quite tiny, you need to tidy them up before importing into the CFDs or like a simulation software, as it will give you a huge, and either it will make the solution won't converge, or it takes forever, or it even won't start and give you some errors, which is not easy to correlate to what's happening. But if you remove that small island first, then you get more and more and better results. I think this is the main issue. That means we need some tidy up of these unwanted things, but that won't affect the simulation, because if they are isolated features or small features, they won't, the effect on the final simulation will be really tiny. And yeah, I think that's the main.
That's something similar to when we do mechanical analysis. Where do you get the material properties for things on such a small kind of length scale, or do you just use standard bulk material properties and kind of ignore scale effects?
So the material property I use is, for example, the conductivity and the ionic diffusion coefficients inside of the electrolyte. I think they are inherent or intrinsic material property, let's say for the electrolyte itself or for this kind of active material, they are independent of how large your particle is used. And then apart from that, the material property like the porosity, with the advantage of image-based simulation is that we don't need to assume volume average parameters such as particle size, right? Because all the particles, they are directly resolved, they are embedded into the simulation and the porosity or pore size distribution. We didn't use any of the volume average parameters. Then what else? Like what I can think of is the diffusivity in the solid state in the particle. They are all measured using a whole electrode. And I think they are more or less constant no matter what kind of the simulation volume we use. So yeah.
Okay. Thank you. So we've got a question from James in Southampton. So yeah. Thank you. Really interesting presentation and paper. And I know James is working on a similar kind of field. How long did the COMSOL simulations take to solve, and what computer resource were you using?
Yeah, I forgot to mention that. So my simulation, because I use nano-CT and to resolve some fine structures. So the total element number is about, average is about 25 to 30 million. I know it's a lot, but because of the tiny features, we need to make that structure fine. And then I use the UCL supercomputing computer, high performance computing service. So we have the main issue of the simulation, which limits the time of the convergence, is the memory. Because of the high element number, if there's an overflow of the memory, it will take much longer than any other factors. Like the computer I use has like 32 cores, and the memory, total memory for this model, the machine's memory is about 256 gigabytes. But what is required for this kind of size is 100 gigabytes. I try to use different computer, let's say sometimes the memory can overflow. But if the memory is high enough, it's not overflow. So this model takes about 10 hours to finish.
Okay. Thank you. I don't see any final questions, so I'll say thank you very much for your interesting presentation.
Thank you. Yeah, you are also welcome to send me emails to continue our discussion. I'm more than happy to answer your questions afterwards.
Great, and I'm sure people kind of stick around a bit at the end to chat more.